Hey everyone, my name is Chris. I'm a fourth year PhD student working with Matt Saltzman at Ohio State in the School of Earth Sciences, and I'm making a video to take you through some of our lab spaces and hopefully teach you something about what we do. So in the Saltzman group, our focus is to understand the causes of global climate change that happened hundreds of millions of years ago. And so to do that, we study specific aspects of ocean chemistry that are preserved in rocks. Because if you want to study the oceans from 450 million years ago, the only thing that's left are rocks that formed from the oceans. So what we focus on is primarily limestone, because this nicely preserves really what we're interested in. So you see this piece of limestone happens to have a bunch of fossils in it, pieces of coral and little bits of shells. And so actually this piece is cut and polished the other side, so you can see nicely all the little pieces of stuff in there. And so what we do to analyze the chemistry of these rocks is, so here's another piece of limestone. We drill out a little bit of powder, just using just a regular hand drill. And so, your powder, once you have it, you really don't need much for most applications. So just about that much. And then we can analyze the chemistry of that powder and learn something about what was happening a long time ago. And I'll show. We're going to get some more on that. The other thing that we also can measure the chemistry of, sometimes the chemistry of rocks gets kind of messed up. So the other thing that we look at are the chemistry of tiny fish teeth that are actually preserved in the rocks. And so this is a printout of them. They're called conadonts, and they're about dust to breadcrumbs sized. So there's some dust on this table. So if I had a bunch of conadonts on my fingers, they would look, they'd be about that size. So we have lots of limestone in here to analyze. This is from all around the world. These are some samples I collected in Sweden the other summer. We have samples from around the West Virginia and Maryland and Pennsylvania and out west, Nevada, and all around. So we keep those samples in here and we drill them in here if you want to get it out of rock. If you want to measure fish teeth, first you got to get the fish teeth out of the rock. And so we have a preparation space it's called Conadont Extraction. So how do you get dust-sized fish teeth out of a chunk of limestone? Well, first you've got to break up the piece of limestone into smaller pieces of limestone. So we have a rock crusher that's probably from the 1950s, and you can guess how that works to break up pieces of rock. So what you do is you break up big chunks of rock into smaller chunks of rock, and then you put them in buckets. And I'm not going to open this bucket because it's full of acid. Put them in a bucket full of acid, and you let it sit for a couple days. And so most of the rock dissolves away. But fortunately, the fish teeth are made of a different mineral than the rest of the rock, and so they are actually left behind. So those little coffee filters that are rolled up in the corner are actually full of whatever the sediment that's left at the bottom of the bucket. Once the rocks are all dissolved, we harvest that sediment, and in there is a bunch of fish teeth, as well as a bunch of other stuff you don't want. So this will mark part one of the tour, and next we're going to go over to the clean lab space to see, once you have whatever your sample is, either it's rock powder or tiny fish teeth, we'll see what we do with that next. So now we're in our clean lab facility. If you didn't think that I looked like a scientist before, hopefully you do now. Contamination is a major concern for the kind of work that we do because the chemical signals that we're trying to measure are in extremely trace quantities in limestone. So if, say, a fleck of dust were to land in your sample, now you are measuring dust instead of limestone. So we take all the measures that we can to avoid that, and that includes trying to prevent you carrying dust into the lab. Also, all the air in this lab is supplied through HEPA filters in the ceiling, so it is a remarkably clean facility. So first thing you do, you come in with your sample, whether it's tiny fish teeth or rock powder, and you've got to weigh it out. So we have several balances here, some of which are wrapped up. But these are so sensitive that we keep them within a wind shield, so even small amounts of ambient air flowing through won't disrupt it. And also they're used on a vibration dampening table. This one in particular is our microbalance, and it's sensitive out to about 5 or 6 decimal places, so extremely powerful weighing ability. Then the next step is to dissolve your sample in some acid, and the goal here is to separate these specific chemical signals that we're talking about. So, because I told you that they're in very trace quantities in limestone, and so you need to separate them from all the stuff that you don't care about. So, you can do that by, and I won't get into all the specifics of it, but you dissolve your sample in acid, you drip it through some powder that's coated with some kind of magical chemicals that can separate out really trace compounds, and so then basically what you end up with, here it is, what you end up with is, I don't know if you can see, there's a couple flecks of black stuff, red-brown stuff in there. So that is pure, in this case, that is pure strontium. It's element strontium that's been separated from a sample of rock powder like the one I showed you over in the rock room. So using this facility and the equipment that we have in here, we've been able to separate out this element that we're now going to take over to our analytical facility and try to measure the chemistry of it. And I'm just sort of moving around and getting other shots of the space. So let's move on to the next room then. Okay, so by this point you've separated your, say we're measuring strontium. And so we've separated strontium, and if you remember in the last room, it just looked like the little fleck of dust. So now our goal is to put that fleck of dust into this machine and analyze its chemistry. So how do you do that? Well, first, you have to dissolve that fleck of dust in a droplet of acid. And so when I say a droplet, I'm talking about like when you spit when you're talking, like that amount of, that volume of liquid. So you dissolve your sample, which is weeks worth of work, in that amount of acid, and you drip the acid, see if I can even focus this, you drip the acid onto this tiny ribbon of metal that's pure rhenium metal. And so the idea is, so now you've coated this piece of metal with the element that you're trying to analyze, and so what will happen when we put it into this machine is an electric current is passed through
that piece of metal, and it gets really hot and it lights up. So it's just like what happens with an incandescent light bulb. So that's a strip of tungsten metal instead of rhenium, but it's the same thing. So pass a current through it, it gets really hot and it produces a lot of light. And so when it gets really hot, your sample, which is coating the piece of metal, basically all the chemical bonds in your sample are ripped apart. So the term is it ionizes. So it is atomically destroyed. Well, at least ripped apart. And so that happens in here. And so so now these are charged particles. It's still your sample, but they're in ionized form. And so they shoot down through a tube that goes through here, and so you see a tube that goes. So this is a giant electromagnet. It weighs about 1,000 pounds, and so what happens is this magnet is going to push that beam of ions along this tube. So they were flying straight. The magnet pushes all of them, and they go to the right. So the tube curves around, and that beam of ions is going to crash into detectors in this housing here. And so what we're looking at is different masses of this element. And so if you imagine, so say like automobiles, you have different masses of automobiles. You have cars, think about like a sports car versus like a big pickup truck. So if you were driving a sports car and a pickup truck around a sharp bend, which one do you think is going to end up taking a wider turn? Well, the pickup truck weighs a lot more, so it takes a wider turn. And so basically the similar thing happens here. So the heavier things, the beam kind of splays out. And so then the detectors are positioned where the different masses are going to fall in this housing. And so then we can count the number of different atoms of different masses. And so then, here is Samantha, who has been measuring on the machine. She has spent a lot of time in that exact position. And so then, like you can see on her screen, then you have made a measurement. So this completes the journey from rock to measurement. And so if we make enough of these measurements through time, we can look at changes in certain chemical signals preserved in rocks that formed in the oceans from hundreds of millions of years ago. And that helps us to learn about what was happening with the climate system and ultimately with the Earth system during that time. So thanks for watching, and I hope you learned something. And if you have any questions, please let us know by leaving them in the comments, or you can send me an email at conwell.30@osu.edu, and I'll put a link to that. So thanks.